Hello, this presentation is about my recent work which I presented in ISBI 2021. The title of my research is Unsupervised Deep Learning for Accelerated High Quality Echocardiography. I am Shujaat Khan and my co-authors are Jaeyoung and Professor Jong Chul. We are associated with Bioimaging Signal Processing and Learning Lab at Department of Bio and Brain Engineering, KAIST. In ultrasound imaging, there is a trade-off between visual quality and temporal resolution, which is a bottleneck for many echocardiography applications. Conventional acceleration methods such as multi-line acquisition (MLA) does not remove noise and only work for limited acceleration factors. To improve the performance of multi-line acquisition, various machine learning algorithms have been developed. However, all the known methods are designed to improve the acceleration and they remove the blocking artifact but does not remove the speckle noise. Furthermore, the classical machine learning based algorithm required high quality paired data, and the typical type of data that format that is used for known machine learning algorithms is in the form of RF channel, which is a raw data, or baseband IQ signal. Unfortunately, in many lower end commercial systems, access to such data is not available. Therefore, we propose an image domain framework using cycle consistency. Our proposed method can generate high-quality accelerated echocardiography images and simultaneously reduces the blocking artifacts and speckle noise. The method is evaluated on real in vivo and phantom scans and shown to achieve notable performance gain compared to classical methods such as MLA. The idea behind proposed unsupervised learning is based on cycle consistency gain. Let's take an example of simple cycle gain where we have two domains, domain A and domain B. One represents the zebra images and the other one which represents the horse images. Here our objective is to convert zebra image to the horse-like images while preserving the content, and we are only interested in transferring the style of the horse to the zebra images. To do this, we arrange two generator in a cascaded fashion such a way that the intermediate result can be used to reconstruct original image, and to ensure this consistency between the reconstructed image and the input image, we have L2 loss. Now to ensure that this fake generated image has the same style as our target domain, we have a discriminator which is trained to discriminate between fake and real images. We have another loss between the generator AB and the discriminator, in which discriminator is forced to produce fake images which can fool our discriminator. This way, there will be a tug of war between the discriminator and generator, and eventually we achieve an equilibrium point when generated images from generator AB has same style as domain B while has the same content as domain A. This simple arrangement of generator and discriminator can work for most of the application. However, to ensure the consistency between our results and to avoid mode collapsing, we arrange them in a cycle consistency fashion where we have four generators. Generator AB is used twice and the same generator BA is used twice in this configuration. And we have consistency loss between our reconstructed results. To train our model, we use loss functions which are represented in the form of equation 1, 2, 3, and 4. And cycle consistency and generative adversarial loss are combined with a mixing parameter of alpha. The same can be understood with the help of optimal transport theory, where we have two distribution and a transfer or transport function generator GAB, and the objective is to minimize the Weierstrass distance between two distributions. To design a method which can generate high-quality echocardiography images using accelerated measurements, we need two distributions. One distribution which mimics our accelerated imaging scenario or a low-quality imaging condition, and the second is our target high-quality imaging scenario. First, we generate RF measurement data using phase array probe. In particular, 96 transmit events were recorded with the help of 64 receiver channels, and for transmit case, we use 128 transmit channels. Each transmit event data is used to generate a single line, hence the method is called single line acquisition method. The RF measurement were processed with the help of delay in sum beamformer DES and later filtered with non-local low rank based despeckling algorithm. To generate our low quality or accelerated echocardiography images, 96 transmit event data was subsampled with the help of 2, 3, 4, and 6 multi-line acquisition. In multi-line acquisition case, for instance, in 2 multi-line acquisition, 48 transmit events of the fully sampled 96 transmit event data was used, and vice versa for case of 3 we use 24 and so forth. This represents our accelerated imaging scenario. The accelerated images are unfiltered images generated with the subsample data of the fully sampled data. This will provide us paired data. However, for training purpose, we only use unpaired images, while the paired data is used for testing purpose. Our data set was acquired from the depth range of 25 to 80 millimeter scans and are scaled to 40 dB dynamic range. For training purpose, 55 phantom and 297 in vivo samples were acquired from 5 volunteers. The in vivo data was acquired from the cardiac region of the volunteers, while phantom data was acquired with the help of ATS phantom. For test purpose, 50 phantom scans was acquired from the same phantom, and 192 in vivo samples were acquired from 2 different volunteers. This will provide us 1760 images for training, 55 phantom, 297 in vivo samples, and 5 acceleration factor. With a similar method, we achieve 1210 images for test purpose. Here again, I would like to emphasize that for training purpose, we only use unpaired images, which means images from different anatomies were used as input and target images. A proposed method uses convolutional neural network, and a generated network is a unit-like convolutional neural network, and a discriminator is a simple convolutional neural network. The same generator is used for converting domain A to domain B and from domain B to domain A, while the same discriminator is used to discriminate between two distributions. Here in this section, the reconstruction result of the proposed method are shown. On the left side, we have B-mode images, while on the right side, normalized residual images are shown. The normalized residual images are generated by subtracting the input and output from the target image. On the left side, we can see that the proposed method, which is designed to produce speckle and blocking artifact-free images for all acceleration factor, in particular for 2, 3, 4, and 6 multi-line acquisition, the proposed method successfully removes the speckle and blocking artifacts. especially in the case of in vivo data. While in the case of phantom data, the speckle noise are removed, but the blocking artifact are still there for the case of high acceleration factors such as 4 and 6 MLA. This can be easily seen in the residual images. The performance difference in the phantom and in vivo case is maybe due to the fact that we use relatively smaller number of images from the phantom, while large number of images were from the in vivo case. This indicates that with large training data, the performance can be further improved. However, for the given data set, our performance statistics are like this. As shown in the table 1, we use 3 quantitative metrics: PCNR, SSIM, and GCNR. In all given performance statistics, the proposed method show significantly improved performance. For example, in the case of PCNR, our proposed method show almost 3 times 3 dB performance gain. In the case of GCNR, you can see that the GCNR is quite similar to the target filtered SLA images. One interesting property of our proposed method is that it has constant reconstruction time, which is around 19.4 millisecond, and it is same for all acceleration factors because the same model is used for all acceleration factors. The study can be concluded as follows. A single convolutional neural network can be used to design a universal image domain based method that can process low quality accelerated echocardiography images to generate high quality speckle and blocking artifact images for variable acceleration factors. By synergistically learning from multiple datasets, the proposed method effectively generates better quality images from as little as 24 transmit events, which is not possible from analytical methods such as multi-line acquisition method. The design was evaluated thoroughly on extensive test dataset, which is composed of in vivo and phantom scans, and standard quality metrics were measured, such as PSNR, SSIM, and GCNR. In all the mentioned metrics, the proposed method show significant performance gains compared to conventional methods. In the current study, we intended to show a proof of concept for unpaired learning for high quality echocardiography, and we believe that the clinical verification is necessary, whether the proposed method can be used to identify anomalies or any pathological patterns in the real in vivo scan data of the clinical patient data. However, in the scenario of our in vivo scan, we notice that the proposed method can successfully mimic the target style for healthy patients. The proposed scheme may have potential or can be used for the design of low-powered, high-quality accelerated echocardiography systems. In this study, the loss function was defined by the cycle consistency GAN, and following references are used. The first one is for the cycle consistency loss, the second for our proposed method that we use for the removal of speckle noise, a non-local low rank based framework for ultrasound speckle reduction. We would like to acknowledge the National Research Foundation, which supported this study. Thank you.